So the first thing you have to do is you do need to figure out what the a value is. Notice that the two numbers that I'm going to be working with here, they're both close to 4. In order to make this into a 4 then, yes, we make a equal 1. So that's the a value using. Now remember what the a is. That's telling you that that's where we want to find the derivative. So we want to find the derivative at the point 1 comma whatever we get for a y there. So proceed from there, find your derivative, find your slope, find your equation. So we find our derivative, then we plug 1 into our derivative, and so we can get a slope then of 1/4.
Yeah.
Okay, we got our slope as 1/4, so we now know that y equals 1/4 x plus b. So now we got to plug in the x and y coordinates of a point, specifically the point at which we are taking this at a equals 1. And when a is 1, what is y?
2.
So notice I'm plugging it into the original equation. So 1 plus 3 is 4. Square root of 4, yes, is 2. So that's the y value you're using. So plug those in to find your b value from there. So we find our b value by plugging in. I wrote it as 1 3/4. You could write it as 7/4 or 1.75. They're all the same. They're all going to work there. So we now know our linearization formula. But remember how we write it. Remember that means that it is L of x equals. So we always want to use L of x for this tangent line equation that we are using to approximate. So L of x here equals 1/4 x plus 1 3/4, or however you chose to write that. All right, now that we know that, we need to go ahead and figure out what our two values are. So what am I going to be plugging in for x for the square root of 3.98?
Negative. No.
Yes, negative 0.02.
Nope.
No.
A lot of us are thinking negative 0.02, but it's not. Because remember, I'm figuring out what can I plug in for x that makes that
0.52.
equal 3.98. It's the 0.98.
Yeah.
Oh, it is? I was right?
So you're going to figure out L of 0.98. And for the other one, what's the x value going to be that gives us 4.05?
05. Negative 0.05.
No, it's
1.05. Because, remember, we're starting with this equation up here. What plus 3 equals 4.05? It's 1.05. So that's how we're getting there. All right, so for this one, we're finding the linearization of y equals x squared at 3, 9. Now notice everything after that is, once we have the linearization, what are we going to do with it? So I don't even need to worry about this yet. And the reason is because I already have enough information up here. I want to find the linearization. Remember, linearization is just a fancy name for equation of the tangent line at that point.
Oh, I just thought
So,
it was slope.
let's find the derivative
Stupid.
and plug in the point that we have. So here's all of our work that gets our equation. Now when we write our equation, what's it called again?
linearization.
It is the linearization, which we represent as L of x. So when you wrote the equation, make sure that you actually wrote it as L of x equals, in this case, L of x equals 6x minus 9. All right, now we can go ahead and take care of the second part, which is to use it to make a prediction about the value of 3.1 squared. All right, so that means I need to do L of what number?
0.1 squared.
What was A?
3.
3. How far are we away from 3 here?
0.1.
Oh, frick.
Wait, would it be negative? Wait, how come we aren't doing it as 9.6?
Because we're not. Wait, what?
9.6.
Because isn't 3.1 squared 9.61?
Yeah, but the point is x at
Now if I do that, we end up doing 6 times 0.1, which is 0.6. We do that minus 9, and then it's giving us a negative 8.4. Wait, that doesn't seem reasonable, does it?
No.
No. What's happening? Well, what does this negative 8.4 actually mean in this kind of a case?
It means that the linearization is negative 8.4.
it basically is like we're that far away from our actual value. As some of you are already observing, I wanted to see if we were thinking it through.
A parabola?
We actually don't want to plug in 0.1. We would actually have to plug in 3.1. Now why? Because we're saying, what can I plug in that makes that equal 3.1? There's no addition or subtraction to have to worry about here. So what do I plug in that makes it 3.1? It's 3.1. So yes, we actually do that here. Why did I do it the other way? Because that's where we're going to be headed today, and something else that we're going to be heading into. And so this 6 times 3.1, that'd be 18.6. 18.6 minus 9 is 9.6.
So when do we put in?
All right, now that other work that we did, it actually is going to be relevant to what we're leading into today. But to get us really in the right mindset for it, I want you to think about what dy and dx really mean, because we've been using those for a while, right? We've had dy over dx. But what is dy? What's dx?
Derivative of y. Derivative.
It's really tempting to think of it, yes, as it's derivative of y and derivative of x. But then dy over dx isn't the derivative of y divided by the derivative of x. It's the derivative of y with respect to x when we do that. And so today we're going to start using these notations in another way. We're going to see why that dy over dx actually is what it is. And I want to just illustrate it first, and then we'll come back to seeing how we can then break some things up in an interesting way. So first up, I want to take a look at how we originally found our derivative. So like you have a tangent line here, which of course the slope is the derivative, drawn in red. The blue function here, that curve, that's the function that we're finding the derivative of. Now notice, between any 2 points on that curve, so we got this point and this point, the slope, of course, is delta y over delta x. Now remember, way back when we started off with secant lines, which is what this slope would represent as the slope of the secant line, what were we looking to try to make happen with that delta y and delta x in order to make it the actual derivative? Well, remember how we kept trying to move this point closer and closer over here? Remember how you had the difference quotient with h in it? And we were trying to make the h really, really small? In fact, we were looking at the limit as h approached 0, right?
Oh yeah. Limit.
Really, to find that derivative, we found the limit as delta x was approaching 0 in the slope, as that gets closer and closer. So in other words, as we are shrinking this way and getting closer to the actual point here, the slope of the tangent line, we're getting closer and closer to it. Well, the tangent line then is the dx and the dy. Because the slope of the tangent line is dy over dx, because that's the derivative, right? And so dy over dx equals the slope of the tangent line.
Oh, I get it, because it's a squared plus b squared.
And so you'll notice that we have delta x and delta y, and we have dx and dy. So really dx and delta x represent the same thing. But depending on which one we're looking at, dy is for the linearization or the tangent line. Delta y is the actual curve. But of course, as we get closer and closer to where those points are the same point, or in other words, as delta x approaches 0, that becomes the same number. And so that's why dy over dx has always been the derivative. But it turns out that since dy over dx actually represents two different quantities, we can do algebraic work with it. In fact, I can even solve this equation here for dy. I can multiply both sides by dx. And if we do that, we get something called the differential. This should go into your notes. And so we can kind of see that in action here, where if I wanted to actually find where dy is, like how far that distance is, we can see that I'm going to take the slope, and then I'm going to multiply it by dx, because dy over dx, that is the slope, equals, of course, the derivative function, which is f prime of x. So it's all relating it back to the derivative and using now the prime notation with the dy and the dx. So now we can go ahead and start making use of this. We're now going to go back to that last equation that we were just working with, and we're going to find the differential of y equals x squared at 3, 9. So in order to do this, remember our definition of differential is that dy equals f prime of x dx. Okay, so notice I have to figure out what f prime of x is. In this case, that's going to be y prime of 3. So let's go ahead and do that here. We're going to have dy equals the derivative of x squared, of course, is 2x dx. That's the general differential. That is the differential. Now, when we start using it to see how we can do it for something like 3.1 squared, at 3, I could plug that in, but that would tell me the differential at 3. And so I need to then plug in the value at which we're actually taking the tangent. So that is going to be at the 3. So we're going to go dy equals 2 times 3 times dx. Now, what is dx in this case?
We don't know. 3.
We do know.
Point
Because
one. It would be 0.1, wouldn't it?
remember, dx is the horizontal distance between our 2 points. Well, the point at which we have our tangent is 3. We're looking to see what's going on at 3.1.
It would be 0.1.
So then dx is, yes, 0.1.
That's so clever.
And so dy equals 2 times 3 is 6 times 0.1 is 0.6. And so notice this now gives us something else. Now, what does that 0.6 really mean? Well, yeah. Remember that dy tells us the vertical distance when we go between those points. So like when we had the curve and we had the tangent line, dy was how far we're going up between those two. So basically what it's saying is that if we go up 0.6 from the original y value, we will get to our prediction. So what's 9 plus 0.6?
9.6.
A familiar number, right?
Wait, I have a question.
Remember when we did it by the linearization, we got 9.6.
So why do you even teach us the linear?
And so this one's a little different because you're plugging in the given x value, and so you always can have that x living there. In fact, you could even write this, if you had to use it for lots of different values, you could even write it as dy equals 6 dx, and you could just change that dx over and over and over again. But notice the difference between this one and the last one is the last one, when we get L of x, when you plug it in, it gives you the prediction. But in this case, when we plug in a d of x value into that, it just tells us how far away it is. So I'm still having to add the 9 to it. And so we might add then to our notes here that the differential tells us how far our approximation is from the original y value. So we're now going to find differentials for some other equations. Now notice we aren't told a specific point here, so we aren't going to have to plug in any numbers, but we do need to find the equation. All right, and so if we're going to find the differential, remember the differential is the dy. dy really is differential. And so we need to figure out what f prime of x is, and that's going to be times d of x. Or not d of x, rather, dx. So I need to find then the derivative of this. What rule will I need to find that derivative? Yep, product rule. Good, because notice it's 5x to the fourth, and it's times the e to the power of 2x. So go ahead and please find that derivative using product rule. So when we go and find our derivative using product rule, this is what we'd be looking at. The little detail that perhaps a couple of you might have forgotten. Remember, for the derivative of e to the 2x, that's a chain rule situation as well. So multiply by the derivative of 2x, which is the 2 there. All right, now, this is not the differential. It's the derivative, but not the differential. The derivative is what dy equals. Now dy, of course, equals f prime of x, yes, so we're going to plug that in. So 20x cubed e to the 2x. I'm going to go ahead and simplify the second part, though. I'm going to go ahead and do the 5 times the 2 there. So that's going to be 10x to the 4th e to the 2x. But then we still have the dx here to deal with. How do I deal with that? I literally am going to write that at the end. But I don't write it just like that, because that would only be multiplying that much by dx. And it has to be the whole thing. So yes, we do need parentheses around it like that. So that is the differential. You notice that basically it's the exact same thing as the derivative, except instead of writing dy over dx equals the derivative, you're writing dy equals the derivative dx. Otherwise, the same idea. All right, so first thing we got to do for this one, we got to find the derivative. Now, just to make our notation a little bit consistent, I'm going to go ahead and call it dy over dx equals. All right, I need to find the derivative of our natural log here. Now remember, the derivative of natural log is 1 over x. In this case, 1 over 1 minus x squared. But we got to use chain rule. So we got to multiply that by the derivative of 1 minus x squared. Now, of course, the derivative of 1 is 0, but notice what we're left with. Negative x squared to take the derivative. And so we're going to be multiplying it by negative 2x. Now, of course, we're going to need to multiply both sides by dx to actually make it into the differential. So dy equals, and I'll go ahead and put that negative 2x into the fraction, so we'll call it negative 2x over 1 minus x squared dx. And there's our differential. So when working this one through, there's more information given, so it can be intimidating at first, but notice what it's asking. Find the differential and use it. Okay, so the first step is just to find the differential. It's doing the exact same thing that we just did, and those last two equations we just did it with were actually way harder than just cosine of pi x, right? So start by finding the derivative of cosine of pi x. So we find dy over dx. Many of you got negative sine pi x, but remember we still have to use chain rule with that. So I multiply by the derivative of the pi x, so it's going to be times pi. So we can then go ahead and write it as the differential. So I'll call that negative pi times sine of pi x dx. Now, some of you I know were intimidated because you saw this stuff here, right? But notice, the first step was just to find the differential. Okay, we did that. And now it says use it to evaluate dy. So basically, to evaluate it, we're just going to plug in. So we're going to go dy equals negative pi times sine of pi times our x value, which is 1/3. And then that's going to be times dx, which is 0.1. Well, now we need to actually do this, which yes is going to mean that you need to remember your unit circle, because we need to remember what sine of pi over 3 is.
1/2.
1/2.
Okay, so sine of pi over 3, root 3 over 2.
3 over 2.
I was wrong.
And so we're going to end up doing negative pi times root 3 over 2 times 0.1. I want to be able to, I got a fraction there, so I want to treat this as a fraction. So I'm going to call that 0.1 1/10.
Oh.
And so then I can actually just write my answer then is pi root 3 over 20. So it's negative pi root 3 over 20 in exact form. Or you can go ahead and multiply it through and get it as a decimal as well.